Welcome to The Explainer. Today, we're breaking down the hidden engineering in things you see all the time. From balconies to diving boards, we are talking about the cantilever beam, a really simple idea with some seriously powerful uses. Let's get right into it.
So, have you ever stood on the very edge of a diving board, or maybe leaned over a balcony, and had that fleeting thought, how is this thing just floating here? What's actually stopping it from just snapping right off? Well, the answer is all about a simple but super powerful engineering principle.
So here's what we're going to cover. First, we'll nail down what a cantilever actually is. Then we'll get into the forces and moments it has to deal with. After that, we'll look at how to visualize all that stress, get to the core formula behind it all, and then, we'll run a quick calculation just to see it in action. Okay, so first things first, let's lay the groundwork and figure out exactly what we're talking about. What is it that makes a beam a cantilever? It's really this simple. A cantilever is just a beam that's locked down at only one end. That's it. One side is totally fixed in place, while the other side just sticks out into thin air. And that one little detail, that's what creates all the fascinating physics we're about to jump into. And this diagram here shows it perfectly. You can see the beam is anchored solid at point A. That's our fixed end. And point B, way out there, is the free end. This super simple setup, it's the secret behind everything from an airplane's wing to the balcony on an apartment building. All right, so we get what it is. But now let's talk about what happens when you actually put something on it. This is where we get into the invisible world of forces and stresses. So when you put a weight out on that free end, which engineers call a load, and we're showing it here as W, it does more than just sit there. It's actively trying to yank the end of that beam downwards. The beam has to fight back, right? And that internal struggle is what causes it to bend and deflect. Think about it like this. Hold a heavy bag of groceries with your arms stretched all the way out. Where do you feel the most strain? It's not really in your hand, is it? It's deep in your shoulder. That's because the weight is creating this huge turning effect or leverage right at the joint. The beam feels that exact same thing, but at its fixed end. And that turning effect, well, it has a name in engineering, the bending moment. It's basically the measure of the internal force the beam has to create to resist that external load. If you want to design a safe cantilever, you absolutely have to understand and calculate this moment. It's everything. Now, engineers don't just, guess where the most stress is. They actually map it out very precisely. And these maps, or diagrams, are surprisingly easy to understand once you see what's going on. See this triangle at the bottom? That's a bending moment diagram. It's like a visual map of the stress inside the beam. And look, it shows us exactly what we felt with our arm analogy. The stress is zero way out at the free end, B, but it just builds and builds until it hits its absolute maximum right at the wall, at point A. And the fact that this map is a straight line, a perfect triangle, is so important. It tells us the relationship is linear and predictable. If you move twice as far from the free end, you get twice the bending moment. It's that simple. And for an engineer, that predictability is incredibly useful. So, if we can map it, that means we should be able to calculate it, right? And you'll be happy to hear that the formula for finding that maximum stress is, well, beautifully simple. This is the big question. Before you build that balcony, you have to know, what is the maximum bending moment that this beam has to handle right where it meets the wall? And there it is. Seriously, that's it. Moment equals the load times the length. All of that complex, invisible stress we've been talking about, it all boils down to this one simple multiplication problem. So let's just quickly break that down. M is the bending moment. That's the turning effect we're trying to find. P is the point load. That's the force being applied. Like a person standing on the end of a diving board. And L is simply the length of the beam, from the wall to where that load is. Okay, theory is one thing, but let's make this feel a bit more real. It's time to actually put this formula to work with a quick, practical example. Let's pretend we're the engineers, and we're designing some small structure. We've got our formula, M equals P times L. Now let's see how we'd actually use it. The whole process is just 3 simple steps. First, we identify our load, P. Then we identify our length, L. And finally, we just multiply them together to get our moment, M. So for our example, let's say we have a beam that's 2 meters long, and at the very end, we're putting a load of 100 newtons. Just to give you a feel for that, 100 newtons is about the weight of a 10-kilogram object, or something around 22 pounds.
So we just plug those numbers right into our formula. Our bending moment M is going to be 100 newtons, our load, multiplied by 2 meters, our length.
And that gives us 200 newton meters. That's our answer. And the unit itself, newton meters, tells the story perfectly. It's a measure of a force, newtons, applied over a distance, meters. This number, 200 Nm, is the critical value an engineer would need to make sure the beam and its connection to the wall are strong enough.
And really, this brings us to the most important takeaway of all. For a cantilever, it's not just about how heavy the load is, it's about how far away that load is. A tiny weight placed way out at the end can create the exact same stress as a really heavy weight that's close to the wall. That's the power of leverage, and it's the absolute soul of the cantilever beam.
So now that you get the principle, M equals P times L, I'll just leave you with this thought. Look around. When you're out and about, check out traffic lights, construction cranes, even just the shelves on your wall. How many cantilevers can you spot now? Because now you can actually visualize those invisible forces holding everything up. Thanks for watching.